John Wesley Powell didn't set out to discover one of the greatest mysteries of all time, but that's exactly what he did. Powell was a Civil War veteran who lost an arm fighting for the Union at the Battle of Shiloh, but he didn't let his missing limb hold him back. After the war, he became a world-famous geologist and explorer. In May of 1869, Powell set off on the voyage that would make him famous. He led a daring expedition to chart the last unexplored stretch of the Colorado River, a wild and dangerous path that ran through the heart of the Grand Canyon. Of course, Powell had no idea what was waiting for him there. With 10 men, 4 wooden boats, and 10 months of supplies, Powell and his crew launched from the Green River, Wyoming, and began their descent through a twisting maze of canyons and river valleys that no one had ever mapped. The journey was treacherous. They faced brutal rapids, lost boats and supplies, and were constantly in danger of starvation or death. The expedition started with 10 men, but only 6 actually stayed until the end. 3 of Powell's men actually left the party just before the end, fearing they wouldn't survive the Grand Canyon. Tragically, they were killed by local settlers who mistook them for outlaws. But those who did make it to the Grand Canyon with John Powell saw something that none of them could understand or even believe. As we mentioned, Powell wasn't just a veteran and an adventurer, he was also a geologist. So naturally, he was fascinated by the layers of rocks in the Grand Canyon. Eons of Earth's history etched in stone. To a trained eye, every inch of rock told a story millions of years in the making. But Powell's trained eye noticed something deeply disturbing, something he could hardly believe, let alone explain. Entire layers of rock that should have been visible in the Grand Canyon simply weren't there. This wasn't just a bit of erosion. It wasn't a slight blip either. To Powell's shock, he discovered 1 billion years worth of rock layers that should have been there were nowhere to be seen. Powell's discovery came to be called the Great Unconformity. How could 1 billion years of Earth's history simply vanish? This mind-bending gap in the geological record of our planet still puzzles geologists to this day. However, recent discoveries may give us a clue as to what really happened to the missing billion years. So what did John Wesley Powell actually discover? In the Grand Canyon, the rock layers are famously well exposed, stretching over 1 mile high in some places. As Powell studied these formations, he quickly realized that the rock layers weren't continuous in age. They were abrupt jumps in time. He also found that some younger sedimentary rocks like the Tapiot sandstone, Cambrian, 525 million years old, sat directly atop ancient crystalline basement rocks like Vishnu, Precambrian, 1.7 billion years old. This meant that over 1 billion years of Earth's history was missing, an idea that was astonishing at the time. This unconformity is not just a minor crack in the storybook of geology, it's a lost volume. Imagine a book missing a couple of pages. Now imagine entire pages being ripped out of books. It's the same concept. It omits major chapters in Earth's past. Chapters that may have held clues to the origin of complex life, global climate transitions, and tectonic upheaval. Understanding this massive time gap is not just an academic pursuit. It's vital to understanding the Earth's evolution and the processes that have sculpted the planet over billions of years. Besides, it's just very bizarre that so much history could just vanish. In fact, it seems almost impossible. To understand why this is such a mystery, it's important to understand how rock layers such as those in the Grand Canyon form. These layers, or strata, are primarily made up of sedimentary rocks which form through the accumulation and compression of minerals and organic materials over millions of years. The process begins when sediments like sand, silt, and clay are transported by natural forces such as wind, water, or ice, and laid down in layers, typically in oceans, lakes, or deserts. Over time, additional layers accumulate, pressing down on the older ones beneath. Minerals dissolved in groundwater flow through these layers and act as a natural cement, binding particles together to form solid rock in a process called lithification. Each layer represents a distinct environment: a desert dune, a shallow sea, a river delta, and each is a time capsule giving us precious clues as to what the world was like long before humans. Over millions of years, these rock layers can become folded, faulted, or uplifted by tectonic activity. In this way, the strata record not only what got deposited where and when, but also a history of earthquakes, volcanic eruptions, and even more violent events. A great example of this is the KT boundary. About 66 million years ago, Earth experienced one of the most catastrophic events in its history, a mass extinction event that wiped out nearly 75% of all life on the planet, including the dinosaurs. This event marks the boundary between the Cretaceous period and the Paleogene period, hence the name the KT boundary. Scientists now believe that the extinction event was caused by a massive asteroid or comet impact, although other factors like volcanic activity and climate change may also have played roles. The KT boundary was first recognized in the early 1980s by Luis Alvarez, a physicist, and his son Walter Alvarez, a geologist. They noticed the layer at the boundary was rich in iridium, an element that's rare on Earth but more common in meteors. At the time, many scientists didn't accept the idea of an asteroid causing such a mass extinction, but the discovery of the iridium layer helped prove that this is exactly what happened. Through the study of rock layers, geologists can determine the relative ages of formations, learn about ancient ecosystems, and identify changes in sea level, temperature, and atmospheric conditions. But this story isn't always complete. In many places, there are sudden jumps in time, where the rock record skips ahead by millions or even billions of years. To interpret the stories locked within rock layers, geologists rely on the science of stratigraphy and several fundamental principles. In any undisturbed sequence of sedimentary rocks, the oldest layer lies at the bottom and the youngest at the top. This allows geologists to construct a relative timeline. Sediment is initially deposited in horizontal layers. If layers are found tilted, folded, or disrupted, it indicates that they were altered by tectonic or geological forces after deposition. Layers extend laterally over a broad area. If a rock layer abruptly ends or is interrupted, it's likely that erosion or a fault caused the disruption. If a fault or intrusion cuts through the existing rock layers, it is younger than the layer it disrupts. Fossil organisms appear in consistent vertical sequence, allowing layers to be identified and correlated across large distances based on fossil content. These principles provide the toolkit for interpreting Earth's history. But when these principles are applied to areas like the Grand Canyon and a billion years seem to vanish, we're faced with a powerful anomaly: the Great Unconformity. To be clear, other unconformities happen. They may represent periods where no new deposits are laid down or where erosion strips away a bunch of strata, or both. But the Great Unconformity isn't like other little blips in the record. It isn't just a local anomaly either, but a widespread geologic boundary that spans continents. Nowhere is the Great Unconformity more visible than in the Grand Canyon. Here, horizontally layered Cambrian sandstone, shale, and limestone, about 525 million years old, rest directly atop Precambrian metamorphic and igneous rocks that are over 1.7 billion years old. The time gap between these layers exceeds 1 billion years, during which countless geological events could have occurred but left no physical record in the form of rock. But this massive absence isn't just a quirk of the Grand Canyon. The Great Unconformity has been observed across North America, Europe, Africa, and Asia. It is so pervasive that it likely represents a global geologic event or series of events that stripped vast amounts of rocks from the continent. The implications are staggering. During this missing time, supercontinents formed and broke apart, extreme ice ages froze the planet, and early life began to evolve into more complex organisms. But almost all of this record is gone, ground away by forces we are still trying to understand. This raises essential questions. What mechanisms could cause such extensive and uniform erosion? Why does this unconformity occur globally, often at similar depths and ages? And what happened during that last billion years? Several different causes of the Great Unconformity have been proposed, and it is likely that multiple processes worked in concert over time. So let's take a look at these theories. The first theory is snowball Earth and glacial erosion. Between 720 and 635 million years ago, Earth is thought to have experienced severe global glaciation, a time known as snowball Earth. During this period, ice sheets may have covered much of the planet and acted as colossal erosional agents. The glaciers could have scraped away entire kilometers of rock from continental surfaces, leaving behind a clean slate for newer sediment to accumulate. The second theory is tectonic uplift and supercontinent cycles. The formation and rifting of ancient supercontinents like Rodinia may have elevated continental crust above sea level. There have been various different supercontinents, with the famous and most recent one being Pangaea. Some others include the first supercontinent Falbara, Kenneland, Columbia, Panocha, and Gondwana. Once these supercontinents broke up due to tectonic forces, this led to the exposure of rock layers. Exposed rock is vulnerable to erosion, especially over hundreds of millions of years. As Rodinia rifted apart, vast regions may have been uplifted, then worn away before subsiding and receiving new sediment. The third theory is prolonged weathering and erosion. In addition to glaciation and tectonic activity, simple but persistent weathering processes, wind, water, chemical reactions, could gradually strip rock layers away. Over the immense span of time involved, even gentle forces can remove substantial rock volumes. Each of these processes leaves a signature in the rock, and geologists are still uncovering those clues using radiometric dating, thermochronology, and geochemical analysis. The Great Unconformity represents more than just missing rock. It's a window into Earth's most dramatic transitions. During the period this gap represents, life evolved from single-cell organisms to the explosion of complex multicellular life in the Cambrian period. Some scientists believe that the environmental disruption and erosion responsible for the unconformity may have even created the conditions that enabled complex life to take over the planet. By removing weathered rock and exposing mineral-rich crust, erosion may have altered the chemistry of oceans, increasing oxygen levels or introducing nutrients, which in turn could have sparked biological innovation. In this way, the Great Unconformity may be intimately tied to one of the most important biological events in Earth's history. Understanding this erosion helps us refine our models of continental development, tectonic cycles, and paleoclimate. It helps contextualize resource deposits and improves our ability to correlate rock layers globally. Scientists continue to study the Great Unconformity using cutting-edge techniques from uranium dating to 3D seismic imaging. So, which theory is most likely to be correct? A recent study may finally give us the answer to what actually caused the Great Unconformity. A study done by the University of Colorado Boulder reveals the complicated history involved in this gap of missing time. It suggests that the rising up of the ancient supercontinent called Rodinia may be to blame. It may have caused tectonic uplift of some areas and erosion in others. The upheaval likely forced the ground around the Grand Canyon to tear up, which then caused rocks and sediment to be washed away by the ocean. It's a good theory, but it's possible that we may never know the true reason for the Great Unconformity. That's all for this video. What do you think of the Great Unconformity? Do you think we will never know the true cause? Or do you think the answers we are looking for are just out of reach? Let us know in the comments below, and don't forget to like and subscribe to History Snob for more cool historical content. Thanks for watching.